Hi. I am very happy to be here in Riga at YAPC Europe once again. And I'm Jonathan. You may have known me from IRC or commit lists as this unpronounceable name. I like living in European countries that start with an S. I've lived in a few of them by now. I like hiking in mountains. I like cold weather. The sea froze this winter. I was most happy. I like good beer. I like type systems and meta-object protocols and Perl 6. And the best thing is when you put them all together, so you're hacking meta models and type systems in Perl 6 in cold weather with a beer. So I want to talk about quite a few things today, so I best get a move on. Around a year ago, we were here at YAPC, and we were all talking about this thing called Rakudo Star. So the idea was that rather than just putting out these monthly compiler releases, which are very much sort of developer, sort of compiler hacker focused, we decided we wanted to start putting together something more kind of useful and usable. So we'd include documentation in the form of a book, we included modules, we included module installation tool, and so forth. So the idea was that this made it so much easier for you just to get something that you could pick up and just dive into Perl 6. Now, there was a lot of good things that came out of this. Rakudo Star shipped with a lot of features. So a lot of the exciting things that have been talked about in Perl 6, all the multiple dispatch, the class system with roles, junctions, hyper-operators, all the various meta-operators, lazy lists that still do the right thing in eager-ish situations anyway. These things were all there in Rakudo Star. So you could really pick it up and start doing Perl 6 with it. We, in the process of doing that, refined the specification a lot. I sometimes hear people say, oh, they didn't even finish the specification yet, or why don't you release the spec? The answer is, well, if we did that, we wouldn't be able to go and fix the spec in the areas that make it hard to implement or don't work. But a lot of what we did in Rakudo Star was identify those areas, and we made a lot of progress in solidifying the spec. We also drew more people into the community, and we got a lot more feedback through that and more contributions. Now, the feedback told us some stuff we kind of already knew, but that kind of really gave us our way forward. So the bad things, it was kind of slow. When I say kinda, I mean really. It was pretty memory hungry. There was a whole bunch of stuff that we hadn't really looked at in the world of metaprogramming. So the idea of Perl 6 is not just that we give you a bunch of really nice defaults, it's also that we give you the ability to sort of warp the language in the future as well, so that it can evolve without a load of hacks. And then there's all the big end time stuff. So really we delivered something that was kind of interesting, but there was still some way to go. So we sort of took a little, rest I guess. It was pretty tiring doing Rakudo Star. And then it was time to find a way forward. So we kind of looked at this and said, well, why is it hard for Perl 6 to be fast? And one of the most obvious things is that a lot of features, if you just do the literal implementation of them, which is what you want to do when you're sort of trying to make it work, is actually pretty slow. So if we think about adding two numbers together, then naively that's a multiple dispatch to an addition operator, which is a subroutine, which adds the two together, really, and returns the result. Now, of course, if you're doing a multiple dispatch, even if we get it pretty fast, for every single addition operation and comparison operation, that's not going to be that fast at all. Another thing we have to be challenged with is that it can be very, very dynamic. We don't always statically know about what's going to happen at runtime. And even when we do have things that are pretty static, they're actually pretty dynamic as well. So if we sort of think about, well, how do classes work? Well, in a given scope, we know how they work, but that's tweakable by lexical scope. So we sort of need to worry about that as well. So at the same time, this isn't a sort of despair thing, and you sort of look at it and you say, well, actually, there's a lot of sort of silver linings in this as well. So we always know in a given scope what the set of operators we have available are. So if we know enough of compile time, then we can sort of make the decision there and then. Sometimes we don't actually need to know the correct answer at compile time to optimize. We can make a good guess and just make it so we can fall back to some kind of slower path if we guess wrong. And also, we can actually sort of co-opt all of these user customizable things just to make sure they are giving us enough information so that we can actually use them in the compilation process and generate good code too. So a lot of what we had to do over the last year was take a sort of good hard look at our compilation process. Now, typically when you have a compiler, a lot of them just do something like this. They take some source code, they turn it into a tree representation, because trees are really what you tend to want to work with inside a compiler. We transform it between various types of tree, and we emit some low-level code at the end. Now, this is pretty clean. It's kind of pure. It's very easy to sort of test and work with. But for Perl 6, we kind of started to hit the limits of this approach. In fact, we've kind of really been pushing past them already. And what sort of goes really wrong here is that whenever a compiler is compiling some code, it doesn't just have to do the syntactic transformation from the source language to the output language. What it also has to do is, at least to some degree, understand what the program is doing. And when you have to understand something, you have to sort of build a model of it. So the compiler would tend to build a model of some interesting things as it did the compilation. Now, that model can then be used for analysis and optimization and so forth. We were kind of doing this to some degree, but in Perl 6, we have this additional challenge that the programmer actually has a great deal of control over those model objects. So we can't just bake in, this is how a class works. We can't just bake in, this is exactly how the syntax looks. So what we kind of really needed to sort of do was to actually take this boundary, which you normally think of existing between compile time and runtime. So you normally look at it and you say, we compile, and then we get some code, and then we run it. And essentially, that model kind of brings up some problems. One of them is that if you build this compile time model, and it's not the same as the runtime model, you get a whole load of inconsistency. The other thing is that a lot of the time, people grab Perl, they run a script, and they just run it straight off. They don't want to pre-compile stuff and so on. So you end up building the sort of compiler view of the thing, and then the real world. So actually, the thing that we've been largely moving to inside the compiler is actually making sure that those are the same thing. So now, the sort of transformation that we've done over the last year is that our compilation model looks kind of like this now. We sort of have the source code, and we still build these various trees, but we're also building up this whole very, very rich model of the program we're compiling behind the scenes as well. And those are the actual meta objects that represent things like variables, classes, roles, grammars, parameters, signatures, and so forth, that we then operate on at runtime. So this has had some interesting consequences. Much of the complexity that we did once have in the compiler actually has moved out into these meta objects now. So it's been kind of a nicer factoring. And the sort of boundary that we would naturally maybe distinguish between this is the built-in stuff and this is the user extensible stuff has kind of disappeared. A lot of our compiler code is now essentially, you would say, polymorphic as to whether it's a built-in defined class or whether it's some module that redefines what a class means that the user pulled in. But what's really important about this is that we've now got ourselves to a world where we have a really rich semantic model of the program we're compiling. So what we can do now is we can start to do all the interesting optimizations that are based off that. So that was one of the big problems that we've sort of been tackling. The other big problem was actually Parrot's object model. Now, the Parrot.pm provides a whole bunch of stuff out of the box which you can use to sort of get yourself on the way with building a compiler. We've used that and we've benefited from it in that we were able to put stuff together often a lot more quickly than we maybe could have done if we'd had to invent them all from the ground up the first time. The thing is that we'd actually gone well past the limits of what that was kind of built to handle. So, in a way, it sort of committed to too much. It committed to a very class-based view of the world without very much flexibility for tweaking that. It also committed to too little, sort of paradoxically, so that you ended up with a lot of late-bound stuff. And the sort of underlying assumption here was we're writing a VM for dynamic languages. Perl 6 is not a dynamic language. Perl 6, in terms of its types, is a gradually typed language. If we want to write our built-ins in Perl 6 and we want to have all this sort of nice speed, then we have to be able to handle the static things in the way the static languages do. We had some other things like lack of native type support, which kind of was an issue. And it was also kind of a weak base for doing the various metaprogramming things we wanted to do. So, it was kind of a case of, well, if we need something else, then what should it look like? And you start sort of going and shortlisting some stuff that you would like, and you say, well, we definitely need metaprogramming. So metaprogramming is all about putting the user in control of things that you'd normally think are hidden away. So if the user wants to say, oh, when we try to dispatch a method, then we really do this. Or when we try to add a method to the class, this is what we mean. Or, oh, I'd like to make it so multiple inheritance is forbidden. So all of these things are kind of in the metaprogramming world. We needed to do this gradual typing thing, which I mentioned. We also needed to do something called representation polymorphism. This is a very Perly idea because basically there's more than one way to style thing. And in this case, it's more than one way to store an object in memory. If you imagine that you're writing some object which is going to represent a pixel on screen, you want it to have very tightly packed sort of numbers in there because you might have a sort of million of them in memory. If you're writing a system which is going to have objects which contain, say, 100 or 200 different attributes, you really don't want to allocate space for all of them up front if an instance typically uses about 5 or 10. You'd really like to have something different there. And representation polymorphism lets us take a class and say, oh, actually, I'd like to represent it this way in memory instead. And then finally, I realized that we really needed to make sure that all of these objects which describe how things are going to work at runtime. So a meta object is just an object that says what another object's semantics are. But we need these to be available at compile time. So I kind of went to the park and sat and thought for a while. And I sort of realized that what I was really doing was trying to find what's at the heart of object orientation and types. And that was kind of tricky in a way. I mean, you know, if you go to programmers who are well versed in, say, a certain language and ask them questions like this, you'll get all kinds of answers. If I go to a Java programmer and say, what's an object and what's a type, they'll say, well, an object is an instance of a class, and a type is that thing I write to the left of a variable name. You know, if you go and ask a class programmer, they'll say, well, an object is kind of this thing in memory, and this thing we allocate, and it stores the attributes. And a type is kind of defined by its class. Okay. If you go and ask a JavaScript programmer, they'll say, well, an object is sort of something which we can attach properties to, some of which might be executable, and we'll call them methods. And then it has a prototype which tells you how to sort of go and find other things. And types, what are they? So depending who you go and ask, you can get a lot of different answers. And it's not that anyone's wrong or right, it's much more that different languages just have very different takes on object orientation. So what I sort of did was say, well, what can we look for that's common? And the thing I found was what I tend to call the operational view. So if we look at the runtime operations that take place on an object, then we can start to see there's a lot of commonalities. Every language likes to allocate objects in some way. You know, here's a bit of memory, it's an object. Pretty much all of them like to do some kind of state storage. So, you know, here's an attribute, and it's going to live in this little bit of memory here. Generally, they also all have some form of dispatch. That is, how do I call something that can do things with this object? That might be method calls, that might be messages, that might be generic function application in the case of PLOS, which is a very different factoring of this, but they all do basically these three things. And then if you look at types, well, there's really only one interesting runtime thing that you tend to have to do with types, and that's a membership check. That is, given this value, is this type sort of done, or does this value a member of that type? And that gets interesting because after a while you realize that that actually is a question that might be answered by different things depending on what sort of type it is. So if you have a refinement type, that is a type which says these values are acceptable, then it's the type that knows. If you have an object and you're asking it, are you an instance of this class? Well, in that case, the object knows. The class doesn't have a link back to all of its instances that we want to sort through. So that gets kind of curious as well. But essentially, this is the main operational thing we care for. So essentially, from that, you can derive a set of OO primitives. You can say, well, we need some kind of state. We need some kind of way of defining semantics. And we need some notion of membership of one or more types. And every kind of object has this. So if you take this model, you quickly realize that you don't need an object model core to have any of these things in its core. You don't need it to have inheritance in its core. You don't need it to have roles and flattening composition. You don't need the type parametricism to be there. You don't really need the refinement types there either. And interestingly, and probably importantly, you don't need the bits of object orientation that we haven't invented yet to be in there. And this is kind of one of the key things. That actually the underlying model, and the thing that told me was right about it was when I took the model and I was able to implement roles without changing anything in the core. So you may have seen this name. This is the name I gave to the sort of research project, which is now what we run Rakudo on top of. I called it 6 model, and it's kind of a model for 6 objects. And essentially, it's just an object framework. It's that small core which you can grow things like classes and roles and subset types and enumerations and interfaces and all those things off. So all it really cares about is these really common operational things. All the rest, that's sort of punted off to the meta object world. And then it just has a little bit of glue to help us with that process of sharing objects between compile time and runtime. So in the 6 model sort of worldview, there's only 2 things, really. There's objects, and these are the things that can be user held. They have a pointer to something called an S table, which we'll come to in a moment. And they have a pointer to something called a serialization context, which is tied into the way we persist environments between runtime and compile time if we're saving bytecode. And then the rest of this object is under the control of something we call the representation. So essentially what we've got here is the first little chunk of every object in memory just has this sort of common bit of info so we know how to work with it in an abstract way, but we don't say anything about how it's going to be laid out beyond that. And that's where we get our representation polymorphism. That's where we get the ability to maybe store attributes in a hash, or just to store them in a flat, compact layout, or whatever we sort of see as the interesting thing. So if you want to do pretty much anything with an object, you follow this S table pointer, this shared table, and you get to a data structure which we never expose to users. This is sort of an internal detail. And basically, this one just has a pointer off to the meta object, which just emphasizes a completely normal object. Someone asked me in the early days, oh, where's the meta object type? And I'm like, no, it's an object. And then it basically just has a function table which says, how do we do allocation of memory for an object? How do we do attribute storage? That's called the repr. And then we let it hang a little bit of representation data off there as well. The reason it's designed like this is actually because if you get a JIT compiler and it knows the representation, it can go and inline the representation function. And then finally, this thing holds a bunch of caches. So if you think about finding a method, the naive way we'd implement that is that you would take your meta object here, and you'd call find method on it, and you'd pass it the name of the method you want to call, and then it will hand you back a method object. Now you can imagine there's a problem there, because how does that thing know how to find the find method? Well, it has to have find method called on it, so it can go all the way down. So, of course, we can't do that, but we break it with some kind of caching. So, that's the sort of how it looks on the inside. So, this is the sort of thing you find on the representation. Just object allocation, attribute storage. We do a little bit of support for boxing and unboxing objects really fast in there as well, because we always need to be doing that. And this is sort of where we have the GC integration if it's needed as well. It also just has a little bit of glue for handling type changes, but we leave that up to the representation as to how it does it. So that's essentially for handling things like mixins. So really what's kind of curious about this is we've got a complete separation into two parts of the API for how objects work. One half is all about how does memory get allocated and the sort of binding to the underlying virtual machine. The other half is the meta object, which knows the answer to everything else. So how do I dispatch a method? What is this type, this object, a sort of member of, and so forth. So you have this sort of core, but the core doesn't really do much, and at this point you need to sort of grow a sort of what we call a MOP, a meta-object protocol. Now all we mean by protocol is essentially interface, a set of different methods that we can sort of agree that will be available to be called on these meta objects. So the way this sort of looks in the Rakudo one, built on top of 6 model, is that we have these various things that all end in how. Now if you've done a lot of Perl 6, or even a little bit, you might have come across this .how macro. This is the macro that gives you the meta object, and when you do it, you go off and introspect and so forth. But we have one of these for each type of sort of package or meta thing that we have in existence. So when you write a class, behind the scenes we're creating an instance of an object that's called class how, which describes how classes work. If you write a role, then we end up with parametric role how. If you write a subset, then we get subset how, and so forth. So every time you're declaring a type, we're actually getting an object behind the scenes which describes how it works. Now, you might look at this list and say, that's all very well and good, but I know that when I write a class, it has methods. And when I write a role, it also has methods. And when I, or for example, when I write some, many of these, they all have attributes, for example. When I have a class, it does inheritance, and a grammar does inheritance as well. So you might be thinking, well, how do we sort of get some reuse? And the answer is that we actually turn into roles. So as well as all these classes, we have a bunch of roles which provide the various bits of functionality. So most of the meta objects are just this. They're a composition of things like method container. I'm something that has methods. Or multi-method container. Or C free MROs. So that means, when we dispatch a method, we will sort the classes that we search through in this order. Maybe it has the ability to trust another class, so that class can see its attributes. Maybe it supports versioning. And all of these bits of functionality just get composed as roles into the various meta objects. So if I jump over here, so this is the actual code that implements a class, a Perl 6 class, and it's written in NQP, which is a subset of Perl 6. So yes, we're sort of defining Perl 6 classes in Perl 6 here. But essentially what's going on here is we're just composing in all these things which say what a class can do. So you can look at this and you can say, oh, a class has a name. It can be versioned. It can trust. It can have sort of a stash, an underlying package, and so forth. So what you might be thinking now is, well, all of these things that describe how classes work are just objects. And the answer is, well, yes, they are. So if it's a class, of course, you can subclass it. So if you're curious about saying, well, wouldn't it be nice if I tweaked the object system to work like this? Well, you take what classes mean, you write a subclass, and there you go, you've tweaked it. So the other thing that we wanted to do as well, though, was make it so that you didn't have to go and inherit from these things. So if you come up with a completely new object-oriented idea and you say, oh, I'd really like to implement this. I mean, suppose we'd done Perl 6 sort of, 10 years before roles were invented. And we didn't have roles, and someone says, oh, roles, they're really great. Wouldn't it have been good if we'd had them first class in Perl 6? Now we pretty much could have them. So whenever the next cool things comes along, hopefully, we'll just be able to build it in there. Now, one of the things that you then get the question of is, well, what happens if I define something completely new? How does the compiler know how to interact with it? Part of the answer is you implement the protocol, but that's not enough because different types can actually be used in different ways and serve different sort of roles in the language. So we kind of came up with, and I have to thank Larry for the name, these sort of archetypes. So you can go to a meta object and you can say, are you available to use as a nominal type? And if not, do you know how to make yourself into one? So subset types do this. You basically take int, if you write the even subset type, you take int, and you sort of turn it into a, you sort of normalize it, as it were. So just to take a little example of this, I want to just go through what metaprogramming looks like. So here's what we're going to do. We're going to implement method modifiers. If you've used Moose, then you'll be quite familiar with these. And this is just a very quick hack version to do this in Perl 6. What's really interesting, just at the top, we're putting this in a module. So we're writing a module which is going to extend the way our language works. And the idea of method modifiers is that you can write a method and you can say, actually, I want this one to run before the sort of real body of the method. And then you can write an after where we say, I'd just like it to run afterwards. So Perl 6 doesn't have any sort of built-in support for this, but we can write a module. So the first thing that you might have noticed is we have these is after and is before things. So what we do is we add to what we call these trait handlers the ability to recognize these before and after. And then we just have a little helper subroutine which is called add modifier. And you might say, what's it actually being passed there? Well, it's being passed the real method object, the object that represents a method that we'll actually have at runtime. But significantly, this is compile time. So the compiler is going to call this for you. So then we need to attach a modifier. Well, the first thing we do is we say, does it already happen? You'll note in here that we use the $question mark operator, which basically means try and dispatch the method, but if there isn't one, then don't worry about it. So if we find we already have a modifier on this, then we complain. Then all we do is we take the method object and we mix an anonymous role into it, which will let us actually determine the modifier that was set. So there we go. We've attached a modifier. So any class that has this, we can now call .modifier on it and be told after or before. So now we need to customize the way that the Perl 6 class works. Well, what we'll do in this example is we'll just go and write a class how with method modifiers. We'll inherit from meta model class how. So the meta model namespace contains all of these various things I discussed. Now, at the moment, these exist outside of the type hierarchy because they're defining it. So we're also going to just stick this mu on there to say it's the top type. The need to do that may go away. So at this point, what we kind of like to do is start, say, intercepting the way that we dispatch methods so that we can sort of run our befores before and our afters after and still return the result in the middle. Well, it turns out that there's basically two things that we need to do. One of them is that we need to intercept add method. Now, add method is a method on the meta object that gets called whenever we add a method to the class. Now, if you just add the same method twice to a class, it'll actually complain that you duplicately defined it. So it won't let you do that. So what we need to do is intercept it, and we need to say, does it have a modifier? And if it does, all we're going to do is just stick it away in this extra attribute. If it doesn't have a modifier, we'll do call same, and all call same means is just call the method that I overrode. So we'll just do the default behavior. So now we're filing away elsewhere all of these modified methods. So finally, what I now need to do is just sort of fiddle with what we call method table computation. So this method called method table is actually called to make a hash which contains all of the methods that we could call. So what we do is we do call same first, which means get the normal sort of unaltered method table. Then we go through all of the modifiers, and then we make sure that the modifier actually is modifying an existing method. If it's not, then we know we can't do this. Then finally, we do classify. Classify is a Perl 6 built-in, which lets you take an array of things and then find properties the objects have in common and build a hash key on that property. So in this case, we key on the modifier. So what I'm getting is a hash which has all of the afters and all of the befores. So all I have to do at this point is then go and sort of twiddle with the method that's in the method table. So you'll see we pull the normal one out, and then we call this little routine to do the computation. And it just looks like this. So all it's doing is returning a closure, which loops over the methods that we want to call beforehand. It calls the normal one and keeps the result. It uses binding so it doesn't impose a context on it. And it then loops and does all the methods that we want to call afterwards. And then we return the result. So all we've done is, instead of having the normal method in the table, we've got this little lantern that we've put there, which is kind of going to go and do the right thing. And actually, that's almost all. The only thing we need to do now is just tell whatever uses this module, please use my definition of class instead of using your own sort of built-in one. And it does that by lexical scope. So here we just say, oh, for the class keyword, use this. And that's all we need to do. We now have it working, and I actually can run it. Okay, so it ran the before, it ran the one in the middle, and it ran the one afterwards. And that worked. And the module, including all the comments and white space and so on, is just 70 lines of code. So that's not too bad. So I'm just going to finish up with a little bit on the sort of where we are now, and then a little bit about our roadmap. So the status is that Rakudo is using 6 model underneath in the non-branch, and we're about to make that master imminently. This is sort of like imminently as in probably during YAMC. So we now build all of these measure objects in compile time. We now have this very, very rich idea of the program that we're compiling, and even if the user has provided sort of custom meanings for classes, we know about those at compile time as well. Part of what we've done in fixing this is actually improve support for sort of begin and all this meta-programming stuff as well. So this example I just showed you was something that we just couldn't have done before. One of the reasons we wanted to do this was speed improvements. Now this fell into 2 categories. The first was that we really needed this sort of much richer model so that we'd be able to write a really good optimizer. But the second part was that we really wanted to get some direct wins out of doing this as well. So depending on the thing you do at the moment, the benchmark you run, then it tends to be that startup time is about the same, but runtime is decidedly improved. So we took a Mandelbrot benchmark and it ran 4 to 5 times faster. And that largely has fallen out of just an object model switch. So there's been other stuff that we've done as well to improve things, but this is largely focused around the fact that we're just a bunch more efficient with the objects now. Of course, there'll be a few things that we've broken. Thankfully, we have a lot of tests. We have a bunch of modules of tests. I'm really happy that the Perl community is great at writing tests. But the sort of course, we'll have a few things. But if you remember the transition we did from the sort of alpha to the ng branch a while ago, this is kind of rather sort of less messy. We didn't rewrite all of Rakudo. We sort of ripped out the sort of object heart of it, and we reviewed the setting very thoroughly. But in terms of the grammar and the actions, these are pretty much stayed about the same. Or where they've changed, it's been a consequence of what else we were doing. One of the other things that we've done in the course of the refactor is that we now have pretty much everything in the compiler written in either NQP or full-blown Perl-6. We don't actually have any Parrot intermediate representation code in the Rakudo repository anymore. I don't think we have a single .py file. So by doing this, we've actually made it so that we're going to be able to do portability of Rakudo in a sort of lot more easy way. So we've kind of managed to rewrite into a high-level language, but make it faster at the same time, which is kind of a nice achievement. But we're very, very keen to get Rakudo running also on the CLR, on the JVM, and maybe on some kind of JavaScript backend as well. So we've sort of taken a big step in that direction also. So what's our sort of direction from here? I mentioned that we hadn't made a big improvement, or really any improvement to startup time. This is one of the next big things I'll be taking on. So what we really want is that when we build this big, sort of rich environment describing all the objects that we're going to have in sort of metaspace, we'd really like to have a really fast way that we can just save that all down to disk and then just bring it back. At the moment, we sort of reconstruct it in a very event-driven and piecemeal way. But the way it's been factored is such that we can really serialize it all. And that's sort of the sort of next big project. And that's going to be coming in the month or two after YAMC. So that should be a big start at Speedway. I want to get it down to 25% of what it is now, or less. Then, of course, the big task will be writing optimizers. We've got ourselves the ability to do that. But next is, of course, sitting down and writing it. This is where we'll get the real wins. So the 4 to 5 times speed win that we've just got is kind of nice. But this is where we will get more of the order of magnitude one. We also will write an optimizer for NQP, which is the language we implemented the compiler in, so the compiler gets faster too. What we've actually got ourselves now is the information to do the optimization I described right at the start of the talk. So that now when we add two numbers together, we're going to get to the point where we can find at compile time, quite often, the sort of multi-sub which is going to do that addition. And then once we've done that, we'll be able to do the inlining. Inlining is where you take the subroutine you would have called, and you take its body, and you just remove the call. You just take the body and stick it in place of the actual call that you would have done in the code. That means you don't have the cost of making the call, you don't have the call frame, you don't have the garbage collection overhead of clearing up the call frame. So basically, the thing that you wrote in your program as an addition, even though we keep all of the overloading support, actually really will boil down to something fairly low level. So that's kind of where we're heading with that. Now, that's multi-sub inlining. Some people say, well, can we do method inlining as well? The problem with method inlining is that even if you know the type, we accept subtypes of the things we pass in, and that means we don't know where the method dispatch will go. But that's okay, we can guess. And if we guess wrong, we just need to have enough around so we can unguess later on. And of course, we want to do a bunch of work on native types. We've started on this. We're sort of going to head in a nice direction on this one. This should also sort of get us a bunch of big wins, particularly if you're going to have large data sets. But it will also be able to use them inside our sort of internals as well, which is going to be a really big help, because once we start doing this with sort of our own built-ins, then we can avoid a whole load of boxing and objects for the built-ins also. And much, much more. Really, our goal has always been to make a Perl 6 implementation that's stable, that performs well, and you will actually really enjoy using. And that's very much where we're heading. That's very much what we're focused on. We've sort of been there and got the features in, and now we're sort of very, very much focused on the performance, on the stability. The last year has been kind of one of doing a lot of the less sexy work. It's been good fun. But the coming months, as we actually start to take all of this and build optimizers and build all of this cool stuff on top of it, is I think when we'll start to see some really nice performance gains, and Rakudo will take a big leap forwards in terms of usability. Thank you very much. I'm happy to take questions in the minus 2 or 3 minutes I have. Anybody? Okay, please.
This blurring of the line between Parrot and runtime, how does that coexist with the idea there can be multiple implementations of filters other than the two?
That just means that pretty much every implementation is going to be needing to do the same kind of thing as well. I mean, they all do to some extent anyway. And Perl 5 does also. I mean, when you write a begin block in Perl 5, you're doing some runtime and compile time. And really, it's just a case of how far do individual compilers want to go in terms of making them look the same. But I think that every Perl 6 compiler will need to deal with these same underlying issues. And my feeling on the best way to deal with it is that you sort of stop trying to pretend they're different and sort of make them the same. And just sort of different phases of the same, as it were. Anything else? Okay.
You were describing the 6 model as a realistic approach and supporting multiple representations of how kind of images profile which is to represent events. Maybe I should have all the line
Well, I'm sure there's some similarities in approach in various places. I mean, there's no sense in which we've invented representation polymorphism here. You can go back and look at algol and find it there as well. So. What's actually happening is Parrot is looking at 6 model and saying, oh, we'd really like to integrate this. So it's actually become, I mean, it's not my call to make, but the noises I'm hearing are kind of, well, this is better than what we have in Parrot. Let's get this in, and I'm supportive of that. So I'm hopeful that we'll get there. But Parrot tends to have a kind of it has a deprecation policy, so they only like to move so fast. And of course, we're still needing to move very, very fast indeed. So it's kind of easier to sort of do these things broken off and sort of see it trickle back in.